Swayam Prabha. Digital India. Educated India.
Dear friends, welcome back. In our previous lecture, we discussed about the characteristics of infinite wings as well as finite wings, and we related the lifting characteristics of an infinite wing with that of a finite wing, right? So we considered a lifting line theory from which we figured out that as the aspect ratio increases, right? So this is the increasing order of aspect ratio. So the CL alpha decreases, right? The lift curve slope decreases. So this is for a wing of infinite aspect ratio or for airfoil. So this lift curve slope represents an lesser aspect ratio compared to that of an aerofoil. So this is where the finite wing starts, right? This plot, from this plot we are talking about finite wings. So this is the variation of CL with angle of attack, right? So if we can observe, so as the aspect ratio increases, CL alpha increases here, right? So and we have related CL alpha 3D is equals to CL alpha 2D upon 1 plus CL alpha 2D upon phi E AR, where E is a Oswald's efficiency factor and is equals to 1 for, and the limits are less than or equal to 1, where E corresponds to, so E is equals to 1 corresponds to elliptical wing, right? AR is the aspect ratio of the wing, of the finite wing, okay? Right, so now let's look at how can we relate, what are the drag characteristics. We haven't discussed much about drag here in the previous lectures. So let's now relate what are the drag characteristics of a infinite wing as well as a finite wing. Is there any relation between these finite and infinite wings? So that's what we are going to do right now. So we know drag, right? So do you remember? So due to the resultant pressure distribution, so when we consider an airfoil in the flow which is inclined at an angle of attack alpha, right? So there will be pressure distribution as well as shear stress distribution. Resultant of that over this surface will be an aerodynamic force called a resultant aerodynamic force, and the component of this resultant aerodynamic force acting perpendicular to free stream is considered as lift, and a component of aerodynamic force, this resultant aerodynamic force which is acting along the free stream, is considered as drag, right? So drag is component resultant aerodynamic force which is acting along or in the direction of V infinity. Okay. Fine. And we know drag is given as half rho V square S times CD, right? So we are talking about infinite wings. We are considering an aerofoil in the first place. So let us consider this CD as like For infinite wings, the drag coefficient is represented by small lowercase d, right? C subscript lowercase d. So CD is the drag coefficient. So what is the contribution? What do drag do in the first place to the flight vehicle? What does it do? It will retard the motion, isn't it? It is acting against the motion. When we say it is, the flow is in this direction at V infinity, which means the body is also moving in the same direction with the same velocity under ideal conditions, right? That means the drag is acting opposite to your motion, which is retarding your motion in the fluid, right? So drag retards the motion. So what do you remember as soon as somebody talks about retardation in a fluid? So what is the property that helps this to happen? Property of the fluid that helps this to happen? Friction, fluid friction, right? The fluid friction is called viscosity. So viscosity is the major contributor for the drag. Of course, there is pressure contribution as well. So viscosity creates shear stress, isn't it? Shear stress distribution. Okay. So we understood one component of this. If not drag directly, we can say drag coefficient. So is from the shear stress distribution, right? So what is the other contribution? Let us say if there is a component of the pressure, or there is a pressure difference along the flow, right? There is a pressure difference across the body that will also contribute towards drag. If there is a higher pressure difference, higher pressure on the frontal part and the lower pressure on the back part, so that pressure difference along the flow will also create pressure, like drag, right? That pressure difference. So we also have pressure distribution of free stream. So do you remember this pressure distribution? A typical pressure distribution over an aerofoil. Right? So where there is positive pressure acting in the frontal part and then negative pressure So this is the typical pressure distribution. So higher the negative pressure, what do you mean? Higher the negative pressure is a point that corresponds to higher velocity. Am I correct or not? So that point corresponds to a lower pressure point. Higher negative pressure is nothing but lower positive pressure there. Right? So there will be a component. See, there is a pressure, higher positive pressure here and lesser positive pressure on the back side. So this will also create, this pressure difference will also create certain force, right, in the direction of free stream velocity. That is known as contribution of drag coefficient due to, or the pressure contribution of this pressure difference along the free stream towards the drag coefficient, right? Now let us consider, do you remember in the ideal flow theory when you talked about a cylinder, we assumed that there are stagnation points S1 and S2. This is the typical pressure distribution that we discussed. Do you remember that? So we have positive pressure on front and back, and negative pressure on top and bottom, because and the highest velocity is equals to twice that of free stream velocity at point P at 90 degrees, right? Isn't it? So it is same, like the distribution on top and bottom is same, right? In case of ideal flow theory, and then on left and right, or in the direction of flow, the distribution of pressure is also symmetric about this object, right, along the free stream. So this will not create any drag on the object, right? But intuitively we all know that, okay, when there is an object in flow, irrespective of that, there is certain drag, you know, whether so this body object, this body experiences certain drag, isn't it? So this particular, though it is in flow and there is no drag and though no lift, right? Such a condition is known as D'Alembert's paradox, right? So that corresponds to ideal fluid theory or ideal, yeah. Yes. Why we are discussing this? So, but in reality, even at zero angle of attack, so this we are talking about ideal flow theory. But in reality, even at zero angle of attack, there is flow separation at the trailing edge, right? That creates a pressure difference between the leading edge part and the trailing edge part, right? So the pressure difference along the flow direction creates certain force on this body along the flow direction. So that contribution is towards this CD, drag coefficient. So this drag coefficient in the coefficient form can be the drag coefficient because of friction, that is skin friction, and drag coefficient due to pressure difference, right? So what do you call this? It's in the coefficient form, we call it as drag coefficient due to skin friction. We call it as drag coefficient due to pressure difference, right? Or so this first term is known as skin friction drag. Skin friction drag, and the second term when multiplied by the other parameters here is known as pressure drag coefficient or pressure drag due to flow separation. Right? Due to flow separation. Okay. So these two together, like skin friction drag and pressure drag due to flow separation, is known as profile drag. Right? Is known as profile drag here. So the CD pressure. Okay. So for an aerofoil, these are the only two contributions. Like the two contributors for the drag for an aerofoil are the skin friction drag as well as the pressure drag due to flow separation. Right? Okay. So the CD variation can be given as CD at corresponds to alpha 0 plus alpha square, right? Can be with some coefficients zeta 1, zeta 2. So this is a typical pressure like drag coefficient variation with angle of attack in case of an aerofoil. Okay. But what happens when we have a wing? Do you remember? So we talked about lifting line theory, where there is a horseshoe vertex with a bound vertex and then associated with two trailing vertex closing by a starting vertex, right? Characterized a high aspect ratio wings in terms of their lift curve slope. Right? So we can use that theory to characterize that high aspect ratio wings. Am I correct or not? So while deriving the theory, we also witnessed that there is an induced angle of attack, isn't it? For example, consider an aerofoil which is oriented at certain angle of attack V infinity, right, at alpha. But due to this downwash, what happens is, due to the downwash, so the resultant vector will be different here. So this is your V resultant or V infinity prime, right? So which is equivalent to this. So this is V infinity prime. So it induces certain angle called alpha I, right? So this particular angle is your local angle of attack. Right? Do you remember alpha L is equals to alpha minus alpha I, right? So, and which generates a lift. So say this is your lift, overall lift acting perpendicular to the overall free stream velocity, right? But because of the induced angle of attack, alpha I, because of the upwash and downwash, what we have is a change in local velocity, due to which there will be a change in local lift generation. Am I correct or not? So this, a component of this lift that is generated at that particular location, right? So because of the induced angle of attack, so we have a component of this acting in the direction of drag, right? So what we have is there is a induced drag because of the lift in the direction of drag, overall drag of the aircraft, which is L sin of alpha I, right? So CDI is equals to CL times alpha I, assuming small angle of attack, and then from thin aerofoil theory, from lifting line theory, what we have is alpha I is equals to CL upon pi E AR, right? This is at the wing. If you consider the downstream, this is twice, no, two times of alpha I, that is the angle. That. So we will talk about that when we are dealing what do you call it, stability aspects during the second part of this course, right? During the second semester, when we are talking about flight stability and control. So this CDI is equals to CL square upon pi E AR. So what we have in addition is induced drag. So which is due to the upwash and the downwash effects near the wing, right? Okay. So this, apart from this screen friction, see again, if you consider a finite wing, it has the tip vertices so it has tip vertices near the tip chords, right? So those tip vertices will try to drive the air along the spanwise direction, and then there is a wing, right? We have wing which creates an upwash and downwash behind, upwash ahead of upstream of the wing and downwash in the downstream of the wing. So all three together will induce certain angle of attack, or will alter the local flow and produces this induced drag, right? So there is a contribution of lift to the drag. At the same time, there is flow, right? When there is flow, there is pressure distribution as well as shear distribution. So what we have is drag coefficient due to skin friction as well as pressure drag coefficient due to flow separation, isn't it? So the total drag here, so drag coefficient CD for a finite wing is equals to CD naught, or let us say CD because of friction, skin friction F, plus CD because of pressure drag, right, and CD because of induced drag. Okay. So apart from this, so this is okay as long as we are talking about subsonic speeds. So as we enter the higher subsonic regimes or supersonic regimes, yeah, definitely we should talk, yeah, very high subsonic or supersonic regimes, then there is an additional component due to which there is additional drag, right? So there is an additional component of drag because of shock waves, right? We'll talk why there is a shock wave. We'll very soon discuss about this. But for the time being, assume that there are shock waves at higher Mach numbers, so which will contribute towards this drag coefficient, right? So CD I. So these three put together are known as parasite drag coefficient, right? So this, and again, see, profile drag varies with alpha, right? Because see, skin friction has very less effect with angle of attack, but the pressure distribution has definitely has a higher influence, right? So the angle of attack may not influence this skin friction much, but it definitely has a higher influence on this pressure drag due to flow separation, right? So because the pressure distribution changes with angle of attack, isn't it? So and so this particular CD CD because of the pressure distribution, right? So that is why we had that variation of CD with alpha there, isn't it? So the contribution is mainly from this particular parameter, right? And again, for a very thin aerofoil, the CDF can be estimated using analytical relations of flat plate, where 1.324 upon root over Reynolds number. This is in case of laminar flow, right? So if you use this relation, you will be able to estimate the corresponding drag coefficient due to skin friction, right? So that's an approximation that we are using. So that's an analytical relation for flat plate pressure drag coefficient. So these three put together called parasite drag coefficient. Sorry, parasite drag coefficient, which is equals to due to skin friction, drag coefficient due to skin friction, and drag coefficient due to pressure drag coefficient or pressure difference due to flow separation, right? Due to flow separation, and what we have is wave drag, right? Drag coefficient due to shock loss. Okay. So all three put together called parasite drag coefficient, right? So at lower subsonic speeds, this will disappear. Wave drag coefficient will disappear. What we have is CD naught, which is equals to CD friction plus CD profile, or what we can say CD due to, so or the drag coefficient, parasite drag coefficient is due to skin friction and profile drag coefficient, plus you can say CD wave drag coefficient, but at lower subsonic speeds this will disappear. So now we can write this total CD as lift independent drag and lift dependent drag. So all these are lift independent drags, isn't it? So CD wave is because of the Mach number, not because of the lift. So CD profile is because of the pressure difference along the free stream velocity, not perpendicular to free stream, right? And CDF is due to the skin friction, which is a major contributor towards the in the direction of free stream velocity, right? Drag, major contribution of drag toward in the direction of free stream velocity. So all three put together, we can say it's a lift independent drag coefficient, right? And what we have is lift dependent or induced drag coefficient due to lift. Right. So let me name it as CD naught plus, so what is this induced drag coefficient? CDI. Okay. So this is equal to CD naught plus CDI is given by KCL square, right? Where K or CCL square upon pi E AR, right? This is your drag coefficient this particular equation is known as drag polar, which is also written as CD is equals to CD naught plus KCL square, where K is the induced drag correction factor, which is equals to 1 upon pi E here. So K is known as induced drag correction factor. Okay. So this particular relation for a finite wing is known as drag polar. Right? Represents the variation of CD with CL. Okay. So if we look at the variation here, if I plot CD with CL, so how CD changes now in the lower subsonic speeds? So here you can see CD naught is lift independent drag, isn't it? So as the CL changes, we have variation in CD, isn't it? So what we can say is, so if we have CD on the y-axis and CL on the x-axis, right? So what I can say is, so for example, let us consider this particular case. Right? So it's a parabolic variation, isn't it? It's a second order equation in terms of CL. So what you have is, when CL is equals to 0, the corresponding CD is CD naught. Right? This is the lift independent drag coefficient, where when CL is 0, what you have is CD. So this is the corresponding point. And then, yeah. So for the other cases where, let us say if there is, yeah, CD naught, right? So you can see the minimum point is not CD naught, it's something else. Am I correct or not? So if I postulate that with this particular equation, the minimum that I can expect, because CL can never be negative here, so the minimum that I expect is CD naught. Am I correct or not here? Isn't it? Because even CL, if it is negative, the contribution will be positive here, right? So let us assume there is a case where there is a minimum point compared to that of CD naught here, right? So let us say this is that particular minimum point, which corresponds to, so this corresponds to CD minimum, right? CD minimum, and the top point corresponds to CD naught, right? And the corresponding CL for CD minimum is CL for CD minimum, right? Okay. So if we have that, then how can how should I model it? I will change this equation to CD is equals to CD minimum plus K times CL minus CL minimum square, right? So when CL is CL minimum, what you have, the contribution from this induced drag is 0 in this particular equation. It becomes CD minimum. What you have is CD minimum. Right? So, but for modern aircraft with moderately cambered aerofoils, the difference between CD naught and CD minimum is very, very less. Okay, so and the difference can be almost negligible, and we will neglect for the entire course. So from now we will use this particular equation, CD naught plus lift independent drag coefficient and lift induced drag coefficient, to represent CD. Okay. So this is the equation that we are going to use it for the entire course. Okay. And the equation is known as drag polar, as I told you. Okay. So let's now talk a bit about before doing that, let's solve one example problem. So why? Because I want to talk about this wave drag, right? why there is a wave drag at higher subsonic or higher speeds. We'll discuss about this very soon, maybe in next 15 minutes. So meanwhile, we'll solve one example problem related to the concept that we just discussed. So example, I lost track of the example number, so you please kindly continue with the same example. In my opinion, it must be either example 8 or 9, no? Something. Either must be 8 or must be 9. Right? So consider or say consider a delta wing alone UAV with span of 1.5 meters. Right. And a taper ratio of 0.167 and root chord of 0.9 meters. Okay. So the aerofoil used for the UAV has the following lifting characteristics. So alpha at CL is equals to 0 is minus 1.7 degrees, right? And or CL at alpha is equals to 8 degrees is equals to 0.48. This is the data that we have of 4811, let us say, at 8 degrees. So we need to find the drag acting on the UAV flying at a velocity of 50 meters per second, right? Where the drag or the drag coefficient independent of lift or zero lift parasite drag coefficient is 0.02. Right? So what are we asked? So flying at 50 meters per second and at an angle of attack at an alpha is equals to 4 degrees and 6 degrees. Okay. So we need to find the drag acting on a UAV with the given data when it is flying at 50 meters per second, right, at sea level. Let us assume the flight is at sea level and it is inclined at an angle of attack of 4 degrees and 6 degrees. Okay. This is the information that we have right now. So how to proceed with this? What we got to know from the given data is CR is 0.9, lambda is 0.1667 and CT will be approximately 0.15 meters, 0.9 meters. 0.5 where the root chord is not given here. Yeah, 0.9 meters it is given, right? So CR, okay. So CT will be 0.15 meters. Yeah. So, yeah, taper ratio is given, right? Yeah, you have taper ratio information, lambda. So from which you can, so what will be the area of this wing? So in order to find the drag on this aircraft, I need to know what is half rho v square S times CD, isn't it? So I know what is the velocity at which it is flying, and sea level density I know. I need to know what is the corresponding wing planform area as well as CD at alpha 4 degrees and at alpha 6 degrees. So how can I find that? First I'll try to find what is S for this configuration. What is S? So this is a delta wing, right? So we know what is span. By this time you must be comfortable after solving those 3 examples during our earlier lecture. So it was about 1.5 meters, span is about 1.5. We have root chord CR is 0.9 meters, right? And CT now you got, otherwise you can say B upon 6 times, B times, here B times CT plus C, B by 2 times 2 times CT plus CR, right? Isn't it? By 2. This is the area of this trapezium, and the twice the area. This so B by 2 times CT, average of CT CR will be the area of this particular half of the planform, and twice of that will be the entire planform area. What I have is B by 2 times lambda times 1 plus, or CR times 1 plus lambda, right? Am I correct or not? So either you find CT separately, or then just simply use CR, take CR out of this equation. So what you have is, so out of this bracket, so you have this reference planform area in terms of span, which is given, CR is given, at the same time lambda, right? So if you substitute this, what you have is 0.787 meters square, right? So I remember this configuration. We have used it for many experimental purposes. And then, yeah, I got to know what is this. Now I need to know what is CD. CD is equals to, you can express this as lift independent drag coefficient, or zero lift parasite drag coefficient CD naught plus induced drag correction factor K times CL square. I use drag polar, right? Since from drag polar equation. Am I correct? So if I have to find CD at 6 degrees or 4 degrees at alpha is equals to 4, I need to know what is the corresponding CL at alpha is 4 degrees. Am I correct? So what is this CL? CL 3D is equals to CL naught 3D plus CL alpha times alpha, right? CL alpha 3D. So when I change this angle of attack, the corresponding CL value changes. So if I substitute 4 degrees here, I will get the corresponding CL 4 degree given CL naught and CL alpha 3D. So how do I know CL naught and CL alpha 3D? Okay, we know CL alpha 3D is equals to CL alpha 2D upon 1 plus CL alpha 2D upon pi E here, right? So we missed that Oswald's efficiency, and also E is equals to 0.86. Consider E is equals to 0.86 is the Oswald's efficiency factor. Now we need to find out what is AR here, right? So the aspect ratio of this wing is B square upon S, which is 1.5 square over 0.787. So if you find it, it is 2.86. Right. So 2.86 is the aspect ratio for this configuration, and we have E as 0.86, which is. So please make a correction. The CL at alpha 8 degrees is 0.79, right? CL at alpha 8 degrees. It's not CL alpha. It's CL at alpha is equals to 8 degrees is 0.79. So what we have is the following data. So the airfoil data here, right? Okay, so alpha at which CL is equals to 0. So this is minus 1.7 degrees, right? And then CL at 8 degrees. Alpha is equals to 8 degrees. So the corresponding CL value is 0.79, right? This is CL 2D case, right? CL 2D and alpha. So the coordinates here are 8 degrees and 0.79. Okay. So using this data, I'll be able to find out CL alpha 2D, which is equals to 0.79 upon 8 plus 1.7. So I'm multiplying this by pi by 180 to convert it to per radian. Okay. So that turns out to be 4.66 or 4.7, you can say 4.66. So now you have CL alpha 2D. So by substituting in that particular equation, what I can achieve is 4.66 or 4.7 upon 1 plus 4.7 over pi 0.86 times 2.86. So what I have is 2.9 approximately 2.92, right? So CL alpha 3D is 2.92. So now I know what is 3D CL alpha. So I need to know what is CL naught. Or either I can use this formulation, or what I can say is this is equivalent to CL alpha 3D times alpha minus alpha at which CL is equals to 0. Am I correct? Because for aerofoil and wing, we know that alpha at which CL 0 is same. But let us have this approach to find out what is CL naught, right? So I'll try to use this approach. So to find out what is CL naught. So CL naught is equals to CL alpha 3D times alpha minus of alpha at which CL is 0. 2.92 multiplied by 1.7 multiplied by pi by 180. So this must be close to 0. So this is 0.086. CL naught is 0.086. I have CL alpha 2D, which I have used to find out CL alpha 3D. Using CL alpha 3D, I now figured out what is the corresponding CL naught, right? As I know, alpha at which CL is 0. It was given, isn't it? So I know what is CL naught here, 0.086 plus CL alpha is 2.96, and we have variable alpha here, right? Sorry, 2.92 multiplied by, so 4 degrees, which is multiplied by pi by 180. So what is the value of CL at 4 degrees? CL corresponds to CL at alpha 4 degrees is 0.289. Okay, so what we got is CL at 4 degrees, and by substituting that value in the CD, right? So by substituting that, what I have is CD is equals to CD naught is 0.02 plus K, which is 1 upon pi AR, which will be approximately 0.12 times CL square, so is 0.289 square. Now, what will be the answer? 0.03 is the CD at alpha 4 degrees. So I want you to calculate for CD at alpha 6 degrees. Okay. So please let me know what is CD at alpha 6 degrees. And also, don't use CL naught approach. Use the other one that we have discussed. Right? Take it as a homework problem and send it to us. Okay. So now it is clear, right? We have the data, planform like cross-section characteristics, that's aerofoil characteristics, and then data related to the planform geometry, from which we will be able to estimate what is the drag coefficient and lift coefficient at the required angle of attack, right? So now having this data of drag and lift coefficient, I will be able to find out what is the drag acting at that particular velocity, right? What is the velocity here? 50 meters per second. If we substitute that, what is the value of drag acting on this UAV at alpha 4 degrees? At alpha is equals to 4 degrees, and when it is moving at 50 meters per second, what I have is, so 0.5 times 1.2245 is the density of air, kg per meter cube. Yeah, meter cube. So density of air at sea level, and I have 50 square multiplied by CD at alpha 4 degrees, which is 0.03. Multiplied by the corresponding cross section area, planform area, which is 0.787. So what is the value, Prabhajit?
36.15.
So 36.15 newtons, right? So approximately I can say 3.6 kg or 3.7 kg, I can say approximately. So this is the drag that is acting. Now if I have to move at 50 meters per second, to overcome this drag I need to give 3.6 kgs of forward force, which is thrust in our case, isn't it? So I want you to find out for what happens when what is the drag that you need to overcome when you want to move at 50 meters per second at 6 degrees angle of attack for the same aircraft, right? The same fuel. Okay, fine. So let's now get back to that discussion. What happens in the supersonic flight or higher subsonic as well as supersonic flight? Okay. And we are talking about wave drag at higher speeds, higher subsonic as well as supersonic speed. So let us look at how this wave drag is coming into picture as soon as the speed is increasing, right? So same CL, let us assume we are flying at the same CL, same UAV. When moving from subsonic to supersonic, all of a sudden your drag characteristics are changing, including the lift characteristics. But let us concentrate on drag characteristics in the first place, right? So why it is happening? So how do a disturbance in fluid travels, right? That's the first thing we need to understand. So in fluids, any disturbance, right, will travel with the velocity of sound in the form of pressure pulses, right? For example, consider a pool with a like a pool full of water, swimming pool full of water, right? And which is calm and still. Now, if I hit that pool, if I hit a stone into that pool, so you can see there will be ripples forming around, isn't it? So let us say, consider a static fluid. Say this is where you hit the stone in the pool. So you start seeing the disturbance that we have created traveling in the form of ripples, isn't it? Am I correct or not? So similar to that, so the disturbance that we create, for example, will result in the form of pressure pulses, right? For example, what is disturbance here? Instead of now disturbance in this particular ambient condition, what can be a disturbance? If I just push air like this, or if I blow air, right? If I disturb the current state of that of this particular ambient conditions, then we can assume that disturbance will create a local pressure difference, which in turn travels with the velocity of sound in the form of pressure pulses. So this particular disturbance that travels is known as pressure pulses. These are the pressure pulses that propagates the disturbance from at a given location, which we have created at a given location. So this we are talking about a static pressure or pressure pulses in static fluid. and the velocity of this fluid or the velocity of this pressure pulse is equals to velocity of sound in that particular medium. So let us say if it is in air, the velocity of sound in air is about 330 meters per second. Okay. So now, what will be this diameter of this pressure pulse? Let us say it is disturbed at a time, like the time difference between the diameter of a, like, say if you have disturbed at time t0 and it has lapsed over a time delta t, right? Now over this period, say a delta t will be the corresponding diameter of this pulse, isn't it? Where a is the speed of sound, right? Square root of gamma rt, and speed of sound depends upon the type of medium and the corresponding temperature of that medium, right? And delta t is a time, like, after which you are interested in figuring out this particular distance that this particular pressure pulse has traveled. So that will be approximately a times delta t, right? So when you are static, this disturbance travels in all the directions in the form of pressure pulse, right? So irrespective of whether you are static or not, this is how it is going to happen. Okay. So okay, so let us now consider a general example, right? So let us assume we are driving a car or a bike, right, with a helmet on. Okay. So when you sit in the car, so when you are moving, say assume you are on an expressway, so which is about, say, your vehicle is on the expressway. Okay, so I may not be able to draw a good vehicle here, ground vehicle definitely. So say, okay, so you're moving in this particular direction. Let us say there is a bird which is flying here, right? Okay, which is flying far ahead of this car, right? So depending upon the intensity of the disturbance, this may travel to the corresponding, like it may travel certain distance, right? Am I correct or not? But as soon as if the disturbance is in vicinity of this, so this is not affected. The flight of this insect or the bird, which is far ahead of your car, will not be affected much. So when the car comes closer to this bird, so this bird will try. So most of you might have observed this, right? So the insect or the butterfly with a good enough reflexes will try to slip over the vehicle. Right? It will not come and hit your window. It will try to slip over the vehicle, isn't it? If it have a bit of good reflexes, right? So that happens because when you're traveling, the disturbance that you're creating is also moving ahead, right? It is not that it is just moving back, right? It is also moving ahead, and it is moving in all the directions. And the flow particles ahead of the vehicle will try to adjust accordingly. So it will try to figure out where the disturbance is minimal, right? And the fluid particles in the form of these streamlines can bend across this vehicle so that they can smoothly flow over this particular body. Okay, fine. So this is true as long as the disturbance is traveling forward. Let us say if you are traveling at a much higher now, as I told you, this disturbance travels at the velocity of sound, right? Let us say you have increased the speed to a higher amount, right? So this should have a better reflexes, isn't it, compared to that, to escape into the flow. Why? Because the reaction time it will have is much lesser compared to the earlier case. Now assume a case when you are traveling with the velocity of sound, right? The moment it feels the disturbance, you will hit the bird at the same moment, right? It will hit your car, isn't it? So both happen simultaneously. So it will not have the disturbance, and that because of the lack of disturbance, this may not be able to adjust to the flow, surrounding flow happens. That is happening, right? Similarly, the fluid molecules which are ahead of your your vehicle will not be able to adjust if there is no propagation of disturbance ahead of your vehicle. Okay.